Hey everyone, and welcome. Today, we're going to break down one of the most elegant and, honestly, powerful ideas in modern AI, the encoder-decoder architecture. And it all kicks off by trying to solve a really fundamental problem for machines.
So let's start with a basic question. Just think about machine translation for a sec. The English sentence, I am a student, has 4 words. But in French, that's Je suis un étudiant, 5 words. Or what about summarizing a huge, long article into just a couple of sentences? The input and output lengths are totally different. So how on earth does a machine handle that?
Well, the answer is this really brilliant two-part system you see right here. It's made of 2 separate networks that work together. You've got an encoder, whose job is to read the input, and then a decoder, whose job is to write the output. Let's break down how each of these parts actually works.
All right, first up is the encoder. The absolute best way to think about the encoder is as the reader of the system. Seriously, its entire purpose is to just read and understand whatever input you give it. So if you look at the top half of this model, you can see the encoder processes the input one piece at a time. It's usually something called a recurrent neural network, or RNN, which is just a fancy way of saying it's a network that has memory. This lets it understand the context of a sequence, not just individual words. It gobbles up every single part of the input, from the very first word all the way to the last.
So here's the deal. The encoder's whole mission is to read everything and then boil it all down into a condensed understanding. It's not just looking at words by themselves. It's trying to capture the meaning of the entire thing and then distill it into what the source material calls a singular thought.
Okay, so once our encoder has created this thought, it needs to hand it off to the second half of our model. Let's talk about the decoder, which, you guessed it, we can think of as the writer. The decoder, which you can see highlighted over on the right, takes that summary, that singular thought from the encoder, and it just gets to work. Its job is to generate the output we want. That could be anything, right? A translated sentence, a summary, even an answer to a question.
Now, what's really fascinating is how the decoder actually does this. It builds the output one step at a time. And here's the super clever part. To figure out the next word to write, it looks at the word it just wrote. It's this awesome generative loop where it's constantly feeding its own output back into itself to decide what to do next.
So we've got a reader and a writer, but how does that thought actually get passed from one to the other? This connection, this handover, is the absolute heart of the entire architecture.
That connection is something called the context vector. You'll often see it labeled with a C. And this vector is the singular thought we were talking about. It's basically the encoder's final memory, a rich summary of the whole input sequence, all packed into a bunch of numbers. And what's crucial is that this vector is the only thing the decoder ever sees about the original input. This slide really just nails the handover. The best way to picture it is like a relay race, right? The encoder's final thought is the baton, and it's passed directly to the decoder to kick off the writing process. It's this simple, elegant transfer of understanding from the reader to the writer. Now, as powerful and amazing as this whole setup is, it's not perfect. It has one major weakness that's really important to get, and it all comes down to this idea of a bottleneck. Here's the problem. That context vector has a fixed size. It has to cram everything from the input, whether it's a tiny 3-word sentence or a massive 1,000-word paragraph, into that single fixed-length vector. And for really long sequences, that becomes incredibly hard. You can imagine important details just get lost in the compression. And the source material puts it perfectly. It says the limitation is when the size of that context vector C is just too small to do a good job of summarizing a long sequence. This information bottleneck is the key challenge that later, more advanced architectures would have to figure out how to solve.
And that really leaves us with a final big question to think about. If forcing the entire meaning of a long text into one tiny summary vector is the problem, what's the alternative? How could we design a system that lets the decoder peek back at the entire input whenever it needs to instead of just relying on one single condensed thought? That question, right there, is what would lead to the next giant leap forward.